This is the 32nd video in a series that I'm making to support a course in number theory. And we're finishing this course off with a little bit of the theory of partitions and the type of number theory that was studied by Ramanujan. In the last video, we built some identities involving Q-series, and we want to continue doing that today, although today we will end with an application that involves partitions. In particular, we'll end with Euler's pentagonal number theorem. Okay, so let's look at a couple of definitions first, recall something that we saw last time, and then we'll jump into our first big proof, which is the Jacobi triple product. So Ramanujan's general theta functions are defined as follows. So f of a, b, so we've got these two variables a, b. It's defined to be the sum as n goes from minus infinity to infinity of a to the n times n plus 1 over 2 times b to the n times n minus 1 over 2. And this is defined on the region where the product of a and b has modulus less than 1. So there are a couple of very special cases of this which will lead to some nice results. And I've given those right here. So there's phi of q, which is this f evaluated at QQ. So that's going to be the sum as n goes from minus infinity to infinity of q to the n squared. Then there's psi of q, which is f of q cubed, and that's going to be the sum as n goes from 0 to infinity of q to the n times n plus 1 over 2. And there's finally this one which is generally called f of minus q, but that's really f of minus q comma minus q cubed. And that turns into the sum as n goes from minus infinity to infinity of minus 1 to the n, q to the n times 3n minus 1 over 2. And this n times 3n minus 1 over 2 is called a generalized pentagonal number. And that'll actually lead into our big result for the day. So if you're in my class, the first kind of exercise that you will do for today's class will be to show that these are indeed special cases of Ramanujan's general theta function. So in other words, plug QQ in here and see that it collapses to this sum, or this sum, just depending on what you need to plug in there. Now I want to recall a little bit of notation as well, and that's this Pockhammer symbol AQ infinity, or AQN kind of more particularly. That's the product, 1 minus q, 1 minus aq, 1 minus aq squared, and so on and so forth. That extends infinitely. Now, if we had an n here instead of an infinity, there would be n terms in the product, as we saw in the last video. So like I started this video off saying, our first big goal is to prove this thing called the Jacobi triple product. This is a really important tool for proving some product identities involving these Q-series and partitions. So it's a bit of a mouthful, but let's just parse out what we've got. On the left-hand side, we have a sum. It's doubly infinite. The sum as n goes from minus infinity to infinity of q to the n squared z to the n. And on the right-hand side, we have a product of three things. And these three things are each infinite products themselves, given by this formula over here. So we've got minus zq q squared infinity, minus q over z q squared infinity, and then q squared infinity. Where again, like I said, these are expanded like this over here, as we'll see in our proof. So in the last video, we proved this thing which I've written in yellow, and we're going to use this several times as a tool to prove this guy up here. Okay, so let's jump into it. So let's look at this identity which we've derived in the last video. And what we will do is take it and make a couple of replacements. So the replacements that we'll make are q will be replaced with q squared, and then z will be replaced with minus z times q. Okay, so let's see what that does to our identity from last time. So I'm going to start with maybe the right-hand side. So I'll have minus zq q squared infinity just by this replacement. Well, that's actually already a good thing to notice because that's part of our triple product over here. Now let's see what the right-hand side turns into under this substitution. So I've got my sum as n goes from 0 up to infinity of, well, let's see, I'm replacing z with minus zq. So that minus sign is going to cancel, and I will get znq to the n. So that's from this minus z to the n power. Then I'm replacing q with q squared. So that's just going to kill the denominator in this exponent using exponent rules. So that'll be times q to the n times n minus 1. And this is all going to be over q squared n, just because we're replacing q with q squared. But let's notice there's some nice simplification here. Notice this guy is exactly n squared minus n. So that means when we multiply these two terms here, we just get q to the n squared. Okay, so that's a good starting point. And in fact, maybe we'll move this over so that we can save it right here, and then we'll move on to the next step. We just made a substitution into our yellow identity from the last video to build this new identity, which I have in this blue box. Now we're going to hang on to this for a second and look for the parts that might be a little bit problematic and see if we can do some sort of manipulation on those. Well, notice this guy on the left-hand side is in good shape because it looks like this guy over here on the right-hand side of our Jacobi triple product. Furthermore, this q to the n squared times z to the n, that's a really good thing to have as well, because that's exactly what we have here in our sum. So that leaves us with this q squared n to take care of and hopefully rewrite in a way that we get the rest of these terms from this product. Okay, so let's maybe investigate this object. So I'm going to write it as 1 over q squared n. But let's recall what the definition of that is. That's this product of n objects that begins at 1 minus q squared. The next term is 1 minus q squared times q squared, or 1 minus q to the 4th. And it's going to end up here at 1 minus q to the 2n. Good, because we need n total terms. But now what I want to do is multiply by a version of 1. The version of 1 that I want to multiply by will extend this denominator into an infinite product and then give us an infinite product in the numerator that starts at a certain point. So I'll maybe add those terms in orange. So I'll multiply by 1 minus q to the 2n plus 2, 1 minus q to the 2n plus 4, and that's going to extend infinitely. But if I do that in the numerator, I also have to do that in the denominator. So 1 minus q to the 2n plus 2, and then that extends infinitely. So now we can probably rewrite this numerator and the denominator using one of our infinite product notations like we have over here. And in fact, we can do that. So let's notice that this numerator is q2n plus 2 q squared infinity. Now, how do you want to think about this? Well, this thing on the left is like our starting object. We have 1 minus that. And then this q squared, which is the thing on the right, that's kind of like our common ratio, but it's like our common ratio for this product instead of like a geometric sum. So that's exactly what we have going on here. Notice we multiply this by q squared, we get this guy right here. The next term will be, again, this multiplied by q squared, and so on and so forth. So that's the numerator. Notice it depends on n. But our denominator will no longer depend on n. Notice our starting term is 1 minus q squared, and then our common ratio type thing will be q squared again. So that means our denominator is this q squared infinity. Great, so we've taken this denominator right here, which is in our blue sum, and written it as two infinite products, which is good because that's exactly what we want over here. We want 3 infinite products over on the right-hand side. Now, let's look at how this can be applied to what we have in our blue box. Let's notice how this identity can be applied to what we have in our blue box. Well, in our blue box, we have this 1 over q squared n term. If we replace that with this over this, we see that the numerator depends on n, so it has to stay in the sum. But the denominator does not depend on n, so it can be pulled out of the sum. So let's maybe put a star here, and notice that we can rewrite that as 1 over q squared infinity, and then we have this sum as n goes from 0 up to infinity of q2n plus 2 q squared infinity, and then qn squared times z to the n. So again, that's just rewriting it using this line right here. Now next up, I'll notice that this object right here is equal to 0 if n is less than 0. We'll do a little proof of that right here, but the takeaway is that we can add in all of the negative integer terms with no problem because we're just adding a bunch of zeros. Let's maybe check that that makes sense. So if n is less than 0, that means that our product will go something like this. 1 minus q to the 2n plus 2, but this is negative, ... all the way up to 1 minus q to the 0, 1 minus q squared, and so on and so forth. Because we've got a negative exponent here, and we're multiplying by q squared after every step. But notice that this q to the 0 is 1, so that means this part goes to 0. So that proves this little yellow thing that we've underlined. Okay, so what do we want to do from here? Well, we'll erase this board and we'll replace this equation, which is in blue, with the right-hand side switched out with this. But what I'll do is I'll take this thing which is in the denominator of the right-hand side and move it up to the numerator of the left-hand side. So it starts to look like what we have over here. So where are we so far? We have manipulated this yellow sum, which we proved in the last video, to the following thing. It's like a double product on the left-hand side and then this thing on the right-hand side. So we're kind of almost there because we want a triple product. So let's see how things are shaping up and what we're missing. So let's notice that this guy right here is this term on the right-hand side of our goal. This guy right here is this term on the right-hand side of our goal. And then this right-hand side of our equation almost looks like the left-hand side of the goal, except we've got this extra term right here, this q, 2n plus 2 q squared infinity. So that means we need to take care of that somehow. And how will we do it? Well, we'll take our yellow identity, which again, like I've said a couple of times, we did in the last video, and we'll make some replacements, z for something and q for something, in order to build an object that looks like this. So let's look into this and see how we could build an object that looks like this out of these parts right here. But it's actually pretty clear if you look at it. Notice that this q 2n plus 2 q squared infinity is exactly this guy where we have replaced z with q to the 2n plus 2, 2n plus 2, and we've replaced q with q squared. So if we make that replacement, then this thing right here turns exactly into this right-hand side of our yellow identity. So that means we need to make the replacements on the left-hand side as well. Okay, so let's see what we've got. So that'll leave us with q 2n plus 2 q squared infinity equals the sum. And now I have to be a bit careful because I'm making this replacement for n, but I have an n in my identity here. That might seem a little bit problematic, but it isn't, because we can make a change of index into this sum right here. We could switch out all the n's for m's. So that's exactly what we're going to do. So I'll just write the m's here in pink. That is the switch that we're making, but that index change obviously does not change the identity. Okay, so there we've got. That's a little messy, but those are just all m's where the n's were. Okay, so that's going to leave us with the sum as m goes from 0 to infinity of, well, it's going to be minus z to the m, but now z is this q to the 2n plus 2. So that's going to be minus q to the 2n plus 2 to the m power, and then we'll have q to the m minus 1 over 2. So let's write that, q to the m times m minus 1 over 2, but notice we're replacing q with q squared, so that's going to kill this q in the denominator here. And then here we have this is all over q squared m. But now we can put the terms in this numerator together pretty easily. And let's see what that's going to leave us with. We'll have this sum as m goes from 0 up to infinity, minus 1 to the m. I'll just take that out. And then we'll have q to the 2n plus 2 times m plus m squared minus m. So that's just using exponent rules on this. And then this is all over q squared m. Okay, nice. And then from here, we will put this expression, which we have developed for this q2n plus 2q squared, into this right-hand side of our blue boxed equation, which is kind of our current point. So let's see, that's going to give us this sum as n goes from minus infinity to infinity of the sum as m goes from 0 up to infinity of minus 1 to the m. And now I can start putting these things together. So notice I have a q to the n squared times that power of q. So that's going to be q to the, maybe we'll multiply this stuff out, m squared plus 2mn plus n squared, and then plus 2m minus m, so that's going to be plus m, like that. So just to reiterate where that came from multiplying this q to the n squared with q to this large power here, and then doing some like standard arithmetic. Okay, nice. And then next, we've got this z to the n power, and then this is all over q squared m. And now here's where we start to notice some structure. So let's check it out and notice that this guy right here is exactly m plus n squared. So we've got m plus n floating around here. But maybe that means that we need to write this z with that exponent as well. And we can by writing this as z to the m plus n times z to the minus m. That'll give us the same kind of expression there. And then we'll switch the order of the sums and factor out all the stuff that only depends on m. So that's going to give us this sum as m goes from 0 up to infinity. Like I said, we're going to factor out the stuff that depends on m. So that's going to give me minus 1 to the m. And then we'll have z to the minus m, q to the m. So that's this z to the minus m, this q to the m from this m power that's left over right here after doing that factorization over q squared m. So that's all of the m stuff factored out. And then we'll be left with the sum as n goes from minus infinity to infinity of q to the m plus n squared z to the m plus n. So that's the stuff that depends on n. Okay, so now we're in a good spot. Let's recall that this was a fancy way of writing our current total right-hand side of our identity that's being built. So let's start from that point. I'll bring this orange underline up here, and then we will begin manipulating it until we're at the end. So we're almost done. We've got this, which is 2 out of 3 parts of our triple product, is equal to this nested sum. So notice I've got an outside sum with respect to m, and I've got an inside sum with respect to n. But what's important to notice is that this inside sum with respect to n is over all integers. That means I can re-index it so that it no longer depends on the outside sum. We would do that kind of like this. Maybe we would replace n with n minus m. But if n goes from minus infinity to infinity, then that means n minus m also goes from minus infinity to infinity. So that's not really going to change anything. So that's going to allow us to bring this thing down, and it will look like this. We'll have the sum as n goes from minus infinity to infinity of q to the n squared z to the n, which is great because that's exactly what we want on the left-hand side of our product or of our identity. Then next, we'll notice that this first sum, it's not quite what we have in yellow up here, but it's related to another identity, which we proved in the last video. So I'll let you guys dive into that if you need to. So that means we can take this and replace it with 1 over minus q z q squared infinity. So again, using an identity which we had in the last video allows us to rewrite this orange underline in the following way. But now we're done. Notice we just need to multiply this product up here, and the left-hand side will be the right-hand side of our goal product. And then we'll be left with this sum, which is the left-hand side of our goal identity. So that means we finished this proof. Okay, so let's look at a corollary of this theorem. So here's a proposition which is really a corollary of what we just proved, the Jacobi triple product identity. And that is the ability to rewrite these special cases of Euler's theta function in terms of products instead of sums. So this phi of q is minus q squared infinity squared, and then q squared. This psi of q has the following form, and then f minus q can be rewritten as q infinity. Let's notice, and this is actually very important, this is 1 over p of q, where p of q is the generating function for the number of partitions of n. Let's recall that p of q was equal to 1 over 1 minus q times 1 minus q squared, ... Great. That's going to be important for how we finish this video off. Okay, so let's look at a proof, but we're only going to prove this first one. The other two could be thought of as homework problems, or if you're in the class, you're going to do them as in-class exercises. So let's start with phi of q, but we're going to take it from the definition over here. So that is equal to the sum as n goes from minus infinity up to infinity of q to the n squared. But that's going to be equal to this limit as z goes to 1 of the sum as n goes from minus infinity to infinity of q to the n squared times z to the n. But now we've got something that we can apply the Jacobi triple product to, and that is this sum with q to the n squared and n. So we've got this limit as z goes to 1 of minus z q squared infinity minus q over z q squared infinity, and then finally q squared infinity. That was the Jacobi triple product identity. Okay, but now notice as z goes to 1, these two guys limit to the same object, and that object is exactly this one right here. So that gives us minus q squared infinity, and then q squared infinity. And this one is squared like that. Okay, so let's write this out as parts of the product just to get an idea for what it looks like. So this is going to be 1 plus q, 1 plus q cubed, 1 plus q to the 5th, ... So it's going to be that infinite product. So we see that because we've got a minus q here. So we're doing 1 minus q. And then the difference in exponents from one step to the next is q squared. And then this guy right here is going to be 1 minus q squared, 1 minus q to the 4th, ... So we've got some sort of infinite product like that. Okay, like I said, we're going to save these last two for homework exercises or in-class exercises if you're in the class. Okay, so let's maybe get rid of this and then we will prove kind of our nice final result. So as we discussed on the last board, the following identity is very important. So on the last board is written as f of minus q is q infinity, that Pockhammer symbol. But let's recall that this is 1 over the generating function for the number of partitions of n or m, depending on the index. So that's what I've written here. This is 1 over that generating function. But then by our definition of f minus q over here, we have this sum expansion. So now we can maybe clear denominators from the extreme left and right hand side, and we'll see that 1 is equal to this product as m goes from 0 up to infinity of p of m q to the m times the sum as n goes from minus infinity up to infinity of minus 1 to the n q to the n times 3n minus 1 over 2. Now, where would we want to go from here? Well, we would like to maybe smash these together using sort of standard rules for finding products of series. But before we do that, I want to notice that the only way to get a constant term is from the n equals 0 term right here. So we might as well factor this out, 1 plus the sum as m from 1 up to infinity of p of m q to the m. Then we can also think about this as summing over all non-zero integers as well, but I won't encode that there. Okay, so now let's notice that this right-hand side multiplies out as follows. I'll pull the 1 out, and then we'll have this sum as n goes from 1 up to infinity of the sum as m goes from something, I'll put this orange box, to something else. We'll talk about those orange boxes in a little bit, of minus 1 to the m, p of n minus m times 3m minus 1 over 2, and then we have q to the n. So that is from, like I said, multiplying these two series together using the standard rule. Now you might say, well, what are the bounds of this sum? And the bounds of this sum are all integers m such that 3m minus 1 over 2 times m is between 0 and n. Let's notice on the left-hand side, there's no q. There's just 1 plus 0 times q to the 1 plus 0 times q squared, so on and so forth. So every non-zero power of q has this coefficient of 0. That means the same thing must hold over on the right-hand side. So extracting the nth power of q from both sides of this equation will give us the following thing. So we'll have this sum from 0 to n over u sub m, which I'll define those in just a second, of minus 1 to the m, and then p n minus u m equals 0. So we get this bit from extracting from the right-hand side here, and this bit from extracting from the left-hand side here. Then let's define these u's. So our u is equal to m times 3m minus 1 over 2. So it's summing over all possible values like that. So, but the standard thing to do here is to take the 0th term out and then move everything to the other side of the equation. So we can take the 0th term out and then change the sign here. That's like moving it to the other side of the equation if we put a p of n here. Now notice what we've got. We've got a nice recursion for the partition of n, for the number of partitions of n into number of partitions that are less than n. So let's maybe summarize that at the top, and then we will give an example or two. Okay, on the last board we came up with the following really nice recursion for the number of partitions of n. In terms of number of partitions of n that are less than n, differing by this number over here, m times 3m minus 1 over 2. And I want to point out that this number, m times 3m minus 1 over 2, is called a generalized pentagonal number. Okay, so now let's look at this chart of values of um. So notice that m can run over integers. That's built off of the series expansion that we had before. So not just positive integers, but all integers. So that means if we make a chart of values of m, we need positive and negative integers. So I've made a chart from -3 up to 3. Now notice in this expansion, the sign is attached to the m plus first power. So that means if we have an odd m, it's going to be attached to a plus. And if we have an even m, it's going to be attached to a minus. So I've notated that here with these green and blue arrows. Okay, so now we can write down our recursion, or at least the first bits of it. So we have p of n will be equal to pn minus 1 plus pn minus 2. So that's what we get from these two. And it'll be minus pn minus 5 minus pn minus 7. So that'll be, let's see, from those two. And then plus pn minus 12 plus pn minus 15. And then that extends on forever. But it obviously stops once we get to n for use of m. So that's our nice recursion for partitions of n. And this is one version of Euler's pentagonal number theorem because it allows us to write the number of partitions of n in terms of previous partitions that differ by a pentagonal number or a generalized pentagonal number. Okay, so I'm going to get rid of this and we'll look at one more interpretation of this theorem. Okay, so here's another interpretation. So that starts with this identity that we had in an earlier proposition, but now we're going to multiply these out. Obviously, it's hard to write down the exact numbers, but we can interpret what we get from multiplying these out. So this looks almost like the generating function for partitions with distinct parts. And it's actually really related to that. Notice if we multiply an even number of q's, we'll get a positive number. And that'll be like using an even number of distinct parts. If we multiply an odd number of these q's, we'll get a negative number. And that's like using an odd number of distinct parts. So that means this is exactly that type of generating function. So just to reiterate, this is the sum as n goes from 0 to infinity of, I'll call it d even n minus d odd n q to the n, where this d even n is an even number of distinct parts, and this d odd n is an odd number of distinct parts. Great. But now, given that that's equal to this from our previous proposition, we have this nice rule, which is, like I said, another version of Euler's pentagonal number theorem, and that is the difference between these two number of partitions, in other words, the number of partitions of n into even distinct parts and odd distinct parts, is equal to minus 1 to the m time if n is equal to m times 3m plus minus 1 over 2. You might say, well, why isn't it just m minus 1 over 2? Well, that's because m is running over all integers, but if you've got a negative integer, that just has the effect of changing this minus to a plus. So that means we've got m is a natural number here. And then the difference between these two is 0 otherwise. So in other words, if n is a pentagonal number, there is a difference between these two. So in other words, if n is a pentagonal number or a generalized pentagonal number, the difference between these two number of partitions is 1. And which one's larger depends on this parity of our m. But if n is not a pentagonal number, you get 0. Okay, so let's get an example on the board that we'll look at, and then we'll be done. Okay, so here are 2 examples to finish this video off. That's if n equals 6, which is not a pentagonal number. So these two number of partitions should be the same, and they are. So notice if we partition 6 into an even number of distinct parts, there are 2 such partitions. An odd number of distinct parts, there are 2 such partitions. 2 minus 2 is 0. But if we take 7, which is a pentagonal number, it is 2 times 3 plus 2 plus 1 over 2, we get a difference of 1. So partitioning into an even number of distinct parts, we have 6 plus 1, 5 plus 2, and 4 plus 3. An odd number of distinct parts, we have 7 and 4 plus 2 plus 1. The difference there is 1. So I urge you guys to look at some more cases just to get a feel for this working. And that's a good place to stop.